In this video, we're going to take a look at the integral test. Now, before I jump right into the test, let's figure out where this thing is coming from. Let me start with this example. Does the series from n equals 1 to infinity of 1 over n squared converge? So let's start by just thinking about what that series would look like. Let's take the nth partial sum. So if I take the nth partial sum, I'd have 1 over 1 squared, which of course is just 1. Then I'd have 1 over 2 squared, 1 over 3 squared, adding together all these terms until eventually I got to that 1 over n squared. If I were to look at this plotted out, do a quick little sketch. If we think about that n value of 1, we saw that it had a y value, or a summation of 1. If we look at that next partial sum, the 1 over 2 squared, we'd have the second value that we're adding to it at 2, we'd be adding a quarter there. So that would be giving us a total area of 1 1/4. Then at 3, we would have, we'd be adding this 1 over 3 squared, or 1/9. And so the little bars aren't representing my new sums. The total area under these bars is representing my sum. And so it's going to continue to go downwards, and so it definitely is approaching 0. But remember, we saw that the harmonic series 1 over n also approached 0, yet it didn't converge. And so this one, it's not a geometric series. The test for divergence fails. This thing is converging, but we can't say for certain that that means that it does in fact. The series converges. We know 1 over n squared converges, but not necessarily the series when we add them together. So what I want to do for a second, let me define a function. Let's define this function f of x as 1 over x squared. And so if I compare that to my s of n, right, I could take this, this series right here, and I could write it as f of 1 plus f of 2 plus f of 3, all the way down till we got to f of n. And these two things would have to be the same. Given this function right here, 1 over x squared, these two things have to be the same. So I've converted this over to functions, and we know how to work with functions a little bit better, but still, this is kind of a pain to have to find every single function value up to that point. That still doesn't tell me what it's doing. So why don't I instead try to figure out what this would look like in terms of the graph? So if I think about this function 1 over x squared, we know exactly what it looks like. It is a curve that has a vertical asymptote heading to 0. As it's coming down, at 1, we would have the y value of 1. At 2, we'd have the y value of 1/4. 3, we'd have the 1/9. And just continue to press it would continue to go down and down from there. But what I'm seeing is each of these corners, even though my drawing's not precise, each of these corners is hitting exactly on the curve on my box, because at the discrete values, at 1, at 2, at 3, the function is exactly the same as the partial sum. Now, where it gets a little messy is in between, because partial sums, we're only dealing with n's as integers. We're only dealing with those discrete values. Functions deal with all the things in between. So if I'm looking at the area under the curve compared to the area under my boxes, the area under the curve is going to be greater than. But the area under the curve is much easier to compute. I can simply look at it in terms of an integral. But again, if I'm looking at that integral, I can't say that the integral is equal to these function value sums. It is not. What I have to do is I have to say that this is now going to be bigger than. My integral is going to be bigger than what I had from before. Now, the other problem I run into is if I go to 0, or if I just take the integral, say, from 0 to infinity, is we have an improper integral, then it's shooting off to infinity. So I do need to start at 1, which means I'm going to include that first function value of f of 1. And then from there, I'm going to add to that the integral from 1 to infinity of the 1 over n squared, the function that we defined just a few minutes ago. 1 over, x squared, not n squared. N squared, and we have our dx there. So again, this integral right here is clearly bigger than all of these rectangles, which is why I've had to change my equals to a less than symbol. Now, if we look at this integral, this is something that we can compute. Well, we know that f of 1 is just equal to 1. The antiderivative of 1 over x squared would be a negative 1 over x. And we have to evaluate that from 1 to infinity, which really means I need to change this around a little bit. I need to treat it as that improper integral. So that means I must stick my limit in front. I take the limit as, we'll call it c, doesn't matter what we call it. C goes to infinity of this integral from 1 to c 1 over x squared dx. And so again, when we calculate that interval, of the limit, c goes to infinity of negative 1 over x, and we're looking from 1 to infinity, 1 to c. And so when I plug those things in, we'll have our 1 plus limit, c goes to infinity, of negative 1 over c minus the negative 1 over 1. Now 1 over c, that thing is going to 0, minus negative 1 over 1 is going to give me 1 plus 1, which means that this integral with the original function value of 1, this thing is equal to 2. Now again, that's not what our series is equal to. We had this inequality sign in here right here. We saw that we were overcounting in the integral. All of these blue areas here in my picture, this was the amount of overcount. So the integral is giving me something bigger than what I actually wanted. But I do know that that bigger thing is converging, and so as we've seen before with the direct comparison test with integrals, if the bigger thing is converging, well then that means the smaller thing must also be converging. So now what we can say about this original series, does this thing converge? Well, the answer is yes, it does. We've seen that because we looked at the integral. The integral is giving me bigger area. And so that brings us to the integral test. Let's define the integral test. The integral test says, let an be a sequence of positive terms. Suppose that an is equal to f of n, the function of n, where f of n is a positive decreasing function for all x greater than n, where n is an integer. Then the series, the summation from n equals 1 to infinity, an, and the integral from n to infinity, f of x dx, both converge or both diverge. Now notice there are a couple of criteria we have to fulfill. And has to be a sequence of positive terms. If we think about why that would be in our picture, well, we can see if this was alternating, if it's jumping back and forth across the x-axis, well, then we can't just look at this single curve. That curve would have to somehow be jumping back and forth across the axis, and we can't deal with the function's area very easily if it's moving back and forth across the x-axis. So we do have to have a sequence with positive terms. Our function has to be positive and decreasing. Has to be positive for the reasons we just talked about. Decreasing portion because we know if these integrals, if these, I should say, bars were going up in our picture, then it would be diverging to begin with through the divergence test, the nth term divergence test. So we do have to meet certain requirements or certain criteria to be able to use these tests. All of our tests, but this one in particular, we have to be positive decreasing. So let's think of an example. Let's take an example. Let f of x equal 1 over n to the p, then the integral from 1 to infinity of 1 over x to the p tells us what the series n equals 1 to infinity of 1 over n to the p does. Since f of x is continuous, we can see that this function would be continuous as long as we're not at 0, which we're saying x is greater than 1, and it's positive and decreasing. That has to be true. It's obviously a positive number, and those things are going to become smaller and smaller if p has a certain criteria. So we are going to have to set p so that we do in fact have that decreasing structure. If p, if it's not certain conditions or certain conditions aren't met, then it might in fact be diverging. So let's think about this integral right here. We've talked about this thing before when we were looking at our integrals and whether they converge or diverge. I really need to have a dx back here. We've looked at how if certain conditions are met with that p, that we have a convergent integral, and sometimes we have a divergent integral. And when that was true, it converges anytime the p was greater than 1, and it diverged anytime p was less than 1. I'll write that out. Converges when p is greater than 1, and diverges when p is less than 1. So then that brings up the question, well, what about when p is equal to 1? Well, if p is equal to 1, then we simply have 1 over x, which we've talked about that being the harmonic series. Just to write that out, we'd have, if our p was 1, we'd have 1 over n, and if n is going from 1 to infinity, that is the harmonic series, which means it does diverge. So in fact, the only time when this will converge is when that p is greater than 1. This is sometimes called the p-series test, but anytime we have this structure of 1 over our n being raised to a power, we can look at that power and determine very quickly whether it's going to converge or diverge. Anytime that p is greater than 1, converges. Anytime p is less than 1, it does diverge.
So let's take an example. Determine if the following series converges or diverges, and we're going to apply our integral test. So the first thing that I want to think about is I'm going to define a function based on this sequence that will allow me to work with that sequence through an integral. Right? So just switching all my ends out with x's, what I want to think about first, I want to make sure that this function is positive, it's continuous, and that it is strictly decreasing. Those are the three things I want to think about. Now I should point out too that always what I like to do before I ever get started with any convergence or divergence problem is run that nth-term divergence test. Just real quickly in my head, think about, okay, what happens to the limit of this sequence if n goes to infinity? And very quickly, with that degree in the bottom being larger, I see that this thing does, the limit of that sequence goes to 0, which means the divergence test tells us nothing. Had the n cubed been on top, I wouldn't have to apply the integral test or any other tests. I'd just be able to say, okay, limit goes to infinity, therefore the sequence diverges through the nth term test. But this one, again, if we take the limit of this thing, we can see that it's going to 0. So first thing I recognize is that this sequence is continuous, provided that the denominator does not equal 0. So let's think about when this part of it is equal to 0. Well, when we solve the first half of that, we get x is equal to 0. The second would be x is equal to plus or minus I, which of course that's not in the domain of the function, in the domain of when we're considering the real numbers. So the only point at which this thing would not be continuous is at 0. Well, we're looking at the integral, we're going to be looking at an integral from 1 to infinity, because that's where the sequence is going, from 1 to infinity. So the function is continuous for x greater than 0. So perfect. Move on. That's our first condition checked. Next thing we need to make sure is that the function is always positive. Again, at least on our integral. Well, if we think about this, again, our x's, our n values, we're starting at 1. So when we take the integral, we're going to take the integral from 1 to infinity. Our x's, we have x values that are positive. Obviously, this is all going to be positive. If we take 3, multiply it to a positive number, add 1 to it, that's going to be positive. These are all going to be positive, so the function is positive for all x greater than 0. So that's 2 of our 3 conditions met. We do need to show all 3 conditions every single time we apply the integral test. So the third condition we need to show is that the function is decreasing, and this is usually the most work, takes the most time. There's two ways to do this. We can show that the values are progressively getting smaller. So we could show that f of x plus 1 is in fact less than f of x, which we could do that by replacing all the x's in the function with an x plus 1. That's really, really hard to see in this example. Sometimes it's a lot easier to see. X plus 1 cubed and plus an x plus 1. If we could prove to ourselves that that was in fact less than 3x plus 1 over x cubed plus x. I forgot a square on that right there. If we could show that, we would be done, but again, that's really, really challenging. So probably the easiest way to show increasing, decreasing is by taking a derivative. So let's take the derivative of f. Well, this will require that we use a quotient rule. So quotient rule says we'll leave the bottom, we'll take the derivative at the top, which will be a 6x, minus, we leave the top, take the derivative at the bottom, that's a 3x squared, plus 1 times the 3x squared plus 1, all over the denominator squared. Right, so now we've got to show that this thing is always less than 0, or at least on the interval from 1 to infinity, because that's the sequence we're dealing with. Notice the denominator has to be positive. This will definitely be positive because if we square anything, it's positive. So I've really got to think about that numerator a little bit more. Let me multiply out the numerator. And again, I'm just going to worry about the numerator for a few minutes. And so I get a 9x to the 4th minus 3 minus 3, that's going to be a minus 6x squared minus 1. And I've distributed the negative at the same time. So when we simplify this, we can see we're getting a negative 3x to the 4th. The x squareds cancel, minus 1. And again, just paying attention to the numerator, I'm not saying that these two lines are equal, they're not. I'm just paying attention to the numerator, but what I notice is that this is always less than 0 for all x, in fact. And so this shows me that f of x is a decreasing function. That means our sequence, going back to our sequence, this thing right here must be positive, it must be continuous, and it must be decreasing because the function is 2. So we've met the 3 conditions to be able to go on to say that we can apply the integral test. So I'm going to take the integral as we go from 1 to infinity of the, we had a 3x squared plus 1 over x cubed plus x dx. And of course, we can't ever work with an integral when it's going to infinity like that, so I'm going to switch the bounds over. I'm going to call it b. We'll go from 1 to b as b goes to infinity. 3x squared plus 1 over x cubed plus x dx. And this is a great problem for u substitution. If I let the u equal the denominator, x cubed plus x, then du is going to be equal to 3x squared plus 1. And dx. That's exactly the numerator, and so this one works out really, really pretty. Anytime you happen to notice that the denominator's derivative is exactly the numerator, at least pretty close to, it's a good possibility that the integral test might be a good way to go because of the u substitution. So we are going to end up with a 1 over u du. So when we take that antiderivative, still have the limit in front as b goes to infinity, the natural log of the absolute value of u, not that all the u values are going to be positive. I do need to either change the bounds over, I really should have done that in the last step. I need to change these limits of integration over, or I need to plug back in. I really shouldn't have left those limits here. So let's go ahead and let's just for a minute treat it as an indefinite integral. So then if we think about the definite integral, we need to go ahead and replace that u. So I'm going to take the natural log of the absolute value of x cubed plus x, and we're going to integrate that from 1 to b. So again, not completely equal because we're treating that as an indefinite integral. And so then I'm going to plug in lim as b goes to infinity, natural log of b cubed plus b minus natural log of 1 plus 1. And so we'll have the limit as b goes to infinity of the natural log of b cubed plus b goes to infinity, minus natural log of 2. Not really anything we can simplify with the b's, but what we notice is if we plug infinity in, or if we think about what happens to the natural log as it goes to infinity, that thing is going to infinity. And that tells us that the integral diverges. So what does that tell us about the larger problem? Well, it tells us that the series must diverge. And so what we would say is we can apply the integral test to the series summation n equals 1 to infinity of, we had the 3n squared plus 1 over n cubed plus n, since 3n plus squared plus 1 over n cubed plus n is a positive continuous and decreasing sequence. Since we found the integral of 3x squared plus 1 over x cubed plus x dx from 1 to infinity diverges, then the sequence must as well. The series must as well. So that would be a complete answer. When we're applying our tests, we always want to make sure that we have stated the conditions. We've proven those conditions to be true. That's what we did first. There's 3 conditions. Proved those conditions. Then we actually applied the test. So the test said, okay, do the integral, see what happens. We did that, saw it diverged. But then we've got to state what we're using, why we're allowed to use it. So again, I'm stating the test that I'm using, stating those conditions are true, and then I've given the result.